Hello everyone, welcome to lecture 55 in the course Diffusion in Solids. So this will be the last lecture of this week, so it's a tutorial lecture where we'll look at some of the problems related to the concepts that we covered in this week. So the first question, the atomic radius of a solvent metal is 140 picometer. Calculate the maximum allowable atomic radius of a solute atom that can dissolve in the solvent metal to form a substitutional solid solution according to the Hume-Rothery rule. So, we have seen this that according to the Hume-Rothery rule, the mismatch for the favoring the solid solubility should be less than or equal to 15%. So, the mismatch is R solute minus R solvent divided by R solvent into 100. So, if you see then this can be on positive as well as negative side. So, that means the radius of the solute should be like this, either it should be 15 not less than 15% of the atomic radius of the solvent or not greater than 15% of the atomic radius of the solvent. In the question we are asked the maximum. So, therefore, the quantity 140 plus 0.15 into 140 gives us the answer. Which comes out to be 161 picometers. So, moving ahead to question number 2, applying the Hume-Rothery rule, select which of the following statements are correct. So, this question basically is about the Hume-Rothery rule, which talks about the valency, where we discuss that a metal of higher valency can dissolve more into a metal of lower valency. So, the elements in question here, zinc has a +2, aluminum is trivalent, silver and copper are monovalent. So, if we look at this option first, A, that zinc will dissolve more in aluminum than aluminum in zinc. Zinc is of a lower valency +2 than aluminum +3. So, this is not correct. The second is zinc will dissolve more in Ag and then Ag in Zn. This is correct because zinc is +2 whereas silver is +1. Then option C is copper will dissolve more in zinc than zinc in copper. This is again not correct. Fourth is aluminum will dissolve more in copper than copper in aluminum. This is the correct option. So, here the correct options are B and D. Moving ahead, which of the following correctly describes the impurity correlation factor F2 in the vacancy mediated diffusion? The first option, it depends solely on the lattice parameter. It is a function of lattice geometry and vacancy jump rates. It is constant for FCC and BCC lattices, or it is independent of the vacancy exchange rates. So, here we saw that when it comes to the solute diffusion, which is vacancy mediated, then in that case it is not just one vacancy exchange rate that we have to consider. What we typically consider, for example, for FCC, a 5 frequency model. So, where 5 different types of frequencies have to be considered in order to arrive at the correlation factor. And these since this frequency or the vacancy atom exchange rates are also involved. So, it is not just the crystal structure, but it is also these vacancy jump rates which are important. So, the correct option is B. It is not same for FCC and BCC lattice, the lattice geometry is different and clearly it is not independent of the vacancy exchange rates as well. Moving ahead, the question number 4, the correct statement for silicon self diffusion are, or if is, depends on how many are correct. Silicon diffuses much faster than metals at the melting temperature. So, we have seen that this is not correct. Silicon diffusion, self diffusion is much slower than the other metals at the same melting temperature. Then self diffusion in silicon can occur only by interstitial C mechanism. This is also not correct because both the vacancy and interstitial C plays an important role in the case of silicon self diffusion. Third is self-diffusion data of silicon is inconsistent due to oxygen contamination, short life of radioisotope and or implantation damage. This is correct because there is a more scatter in the data that is available on silicon self-diffusion than, for example, if you compare germanium, because of the oxygen is readily can form silicon oxide and that the extent to which it is formed also brings out certain errors in the measurement. Then fourth is the vacancy mechanism of diffusion is dominant at low temperatures. This is correct. At higher temperatures, it is the self-interstitials which dominate silicon self-diffusion. So, the correct answers are C and D. Question number 5, which hybrid solutes diffuse via interstitial substitutional exchange mechanisms? So, this is the direct, we have seen that gold, platinum and zinc in silicon and copper in germanium diffuse via interstitial substitutional exchange mechanism. So, that is B, C and D are correct. The question is here the ratio of impurity diffusion coefficient D2 and the solvent diffusion coefficient D is dependent on. So, in this case the answer got displayed first, but still you have to understand this expression to arrive at the correct options. So, the first option is the correlation effect. So, if you see this ratio of D2 by D, this is equal to F2 by F into W2 by W into omega 2 by omega multiplied by omega 4 by omega 3. And so, therefore, you see that here in this case the correlation effects come into picture because here you have the term F. Then the difference in vacancy atom exchange rates between solute and solvent which is given by this term. Then the interaction between the impurity and the vacancy. So, this is here where you have association and dissociation rate and temperature. So, each of these terms is dependent on temperature. So, you have this ratio dependent on all these terms. So, here are further explanations I have given once again for your reference. Question number 7, the electrostatic model for impurity diffusion attributes the difference in activation energy between solute and solvent 2. So, if you recollect, we had talked about this electrostatic model where the solute diffusivity higher or lower than the solvent diffusivity, that difference is attributed as delta Q. The activation energy difference delta Q is attributed to the difference in the valency between solute and the solvent. So, that is what we discussed, that it is the valency difference between solute and solvent which causes the difference in the activation energy. So, this is the correct option. Select the correct statements about impurity diffusion in aluminum. Most transition elements have lower diffusivity than self-diffusivity of aluminum. This is the option number 1. The second option is most transition elements have higher diffusivity than the self-diffusivity of aluminum. So, in this case the option number 1 here is correct. They have the lower diffusivity than self-diffusivity of aluminum. C, activation enthalpies predicted by electrostatic model agree well with the experimentally measured value. This is not correct. In the case of impurity diffusion in aluminum, we saw that the electrostatic model does not work well and the activation enthalpies are rather scattered. Then fourth is activation volume is positive. So, this is also correct. In the pressure dependence, the activation volumes comes out to be for some diffusers it is almost same as the activation volume for self-diffusion of aluminum. For cobalt and manganese it is slightly higher. Then coming to question number 9, fast diffusion in open metals is attributed to. So, we saw that when we were discussing this, that fast solute diffusion can occur by which mechanism. So, if it has to occur only by the interstitial way, then the radius ratio is too large, such that it is, for example, it may be around 0.83 for gold or so. Then in that case, the gold or these atoms cannot occupy completely the interstitial positions, because then the strain in the lattice will be too much. If you think that it is only by vacancy mechanism, then again the diffusivities are too high to be possible through vacancy mechanism. Interstitials anyways are, the interstitial C are anyways difficult, so that means the self interstitials are very difficult to form in metals. So the correct option here is the dissociative mechanism, which says that the solute is distributed on both interstitial as well as the substitutional sites. Question number 10, determine the configurational entropy of mixing for the following alloys. So you have Al, CO, Cr, Fe, Ni. When it is written in this way, you see that all the atoms are in equal atomic percent. And here the ratio is indicated CO, Cr, Fe, Ni 2.1. And it is aluminum 0.5 CO, Cr, Cu, Fe, Ni. So we saw that the configurational entropy is given by minus R Xi ln Xi. Remember, in this case, yes, it is all equiatomic, but in this case, not all the atoms have the similar composition. Same thing here also. So you have to be slightly careful in calculating the entropy, and you can use R as 8.314 if you are using joules. So these are the values you should get for the change in entropy. Okay. So you can see that when it is the equiatomic, it is the maximum 13.46 joule per mole Kelvin, even though it is 6 elements, but still the entropy is slightly lower. So now coming to next question. Which of the following are postulated as core effects of high entropy alloys? High entropy effect, lattice stability effect, sluggish diffusion effect, or phase separation effect. So here the correct option is A and C. The 4 core effects that are postulated are high entropy effect, which basically tells that due to the high configurational entropy of mixing, the free energy of solid solution formation becomes more negative, because delta G is equal to delta H minus T delta S. And secondly, then the lattice distortion effect is one other core effect, where because there are more number of elements present which have varying sizes, so which will distort the lattice. Sluggish diffusion effect, which is basically to say, because you have so many different types of element, so the diffusing atom will encounter different barriers, different local chemical environment, hence the diffusion may be sluggish. The fourth is the phase separation, so that is the fourth option here, but that is not correct. The fourth effect which is considered as core effect is the cocktail effect, which says that if you mix more number of elements together in a high entropy configuration, the properties that you expect to get are more than just the sum total of the individual properties. Question number 12, the studies on diffusion in high entropy alloys have thus far established diffusion coefficient increases with increasing configurational entropy, diffusion coefficient decreases with increasing configurational entropy, grain boundary diffusion is not significant in HES. The fourth is, it is not just the number of elements that control the diffusion, but nature of elements is also critical. So the C option is not correct, definitely, because we in fact saw the examples of grain boundary diffusion measurements in high entropy alloys. So it does play a significant role depending on the temperatures that are used. Now, for the other 3 options, we have seen that, for example, in this case, we have the 4 component and 5 component alloy comparison of the diffusivities, and we can see that at lower temperatures, the 5 component alloy shows the least diffusivity as compared to pure nickel, iron 40 nickel, COCr FeNi, and then the COCr FeMnNi. However, the effect is not so significant, but still it is the slowest. However, when you go to the higher temperatures, you see it is the 4-component alloy which is the slowest diffusing species, whereas 5-component is not so. So, that means that it is not actually the number of elements which can say that okay, you will always have as you increase the number of elements, the diffusivities will go down. This cannot be used as a blanket statement. So, it is not just the number of elements that control the diffusion, but the nature of elements is also very, very important. So, in this case, the correct option is D. So, I am sorry, this is, so now this is correct, the correct option is D here. Question number 13. Point defects in semiconductors differ from those in metals in which of the following aspects? The first is defects can carry charge. So, yes, it is correct. Semiconductor defects can contain charge. They have plus, minus, or they can be neutral depending upon where the Fermi energy level is located. Defect concentration at thermal equilibrium is lower. This is also correct because of the presence of the covalent bonding, which is much stronger. Then at thermal equilibrium, the equilibrium concentration is less when you compare the metals. Then defect concentration is affected by the position of Fermi energy level. This is also correct because we have seen that that is what gives rise to the charged defects in semiconductors. So, whether they go to the acceptor level or as a donor level, it is decided by the position of the Fermi energy level. Defects do not play any role in diffusion. This is not correct. We have seen that semiconductors, in fact, in semiconductors, not only vacancies, but the self-interstitials also play an important role in several cases. So, the correct options are A, B and C. Question number 14. A student of this course wishes to understand the time dependence of silicon diffusion by performing radio tracer experiments at 1200 Kelvin for 1 hour, 10 hour, 50 hour, 100 hour and 200 hour. Comment on the feasibility of such an experiment. So, here for this there are two things. First of all, the time dependence of diffusion in well annealed metals is not that significant. Diffusion is time independent. In fact, it depends only on the temperature. In certain cases, we will see for example, in glasses next week that there is a time dependence of diffusivity that do come into picture, because with time there are certain relaxations happening. So, in the case of silicon, such a thing is not accepted, not expected rather. So, there is a very little chance that you will get anything out of it. Even if still you want to try, the bigger problem is that we have seen in the case of silicon, where if you want to do the radio tracer experiment, the only accessible radioisotope is 31 silicon, which has half-life of 2.6 hours. So, if it is 2.6 hours, and all these longer time experiments cannot be done, because by the time your diffusion annealing is over, all the radioactive silicon would have decayed. So, then the annealing times, therefore, for the measurements in case of silicon diffusion is extremely restricted. Question number 15, the region Y in the following phase diagram is referred to as. So, this region Y, if you remember, we have seen this kind of diagram when we were discussing the solubility concept. See, what is the so different here? If you see a typical phase diagram, the solver's lines look like this. So, you have it is increasing up to the maximum to the eutectic line, and after that then again it's you will see that the starts decreasing. So, the maximum is usually on the eutectic line, whereas in this case the maximum solubility is between the melting point and the eutectic point. So, this we have seen is known as the retrograde solubility. Then we come to the last question for this tutorial. Silicon wafer is being studied for its oxygen diffusion characteristics at high temperatures, and then a researcher at a semiconductor lab observes that oxygen dissolves interstitially in silicon, forming a bond-centered configuration. The researcher consults data from infrared absorption measurements to determine the oxygen solubility limit. So, the diffusivity of oxygen interstitials in the silicon lattice is measured using indifused oxygen profiles, which are determined by SIMS. Now, the data is shown below. At the processing temperature of 1000 degrees centigrade, calculate the equilibrium oxygen solubility and the oxygen diffusivity. So, you see here that for example, what is given is the temperature range 600 to 850 degrees centigrade, and the diffusivity in meter square per second and solubility per meter cube is given. But what is asked is to calculate at the temperature of 1000 degrees centigrade, and whereas the data that is given is about 600 to 850. So, assuming that this can be extrapolated, what you need to do is, we know the dependence of diffusivity on the temperature. So, regardless of whether it is an interstitial diffusion or substitutional diffusion, the diffusivity follow Arrhenius law. So, we have to plot this log of d versus 1 over t. Similarly, solubility also. So, solubility we have seen indirectly at many instances when we talk about the vacancy concentrations, or when we talk about the solute concentrations, interstitial concentrations, and so on. The solubility depends also exponentially on the temperature. So, it also has a Arrhenius kind of dependence. So, therefore, what we can write, for example, for the solubility, also we can write C is equal to C naught exponential minus H by RT, where H is a kind of activation energy. How do you get this value of H and C naught is if you plot log C equal to log C naught minus H by RT. So, this is the plot shown for your reference, log C over 1 by T. So, the slope will be equal to minus H by R. So, if you do that, then from this slope what you get is this value, and then H is the value of H you can get as 1.1 electron volt. Then log of C naught, the intercept you can use, and C naught is equal to 0.02. Then you can use again the same expression, Ci is equal to C naught exponential minus H by kBT or H by RT, or whatever you want to use, and then you can get the value of the Ci at the 1000 degree centigrade. Now, for calculating the oxygen diffusivity, as I said, you plot log D versus 1 over T, and the slope here you can get from this plot, and from the intercept you can get the D naught. And once you get D naught and Q, again you put this data at 1000 degree centigrade, and you have D is equal to D naught exponential minus Q by kBT, and you can get the value of the diffusivity at 1000 degree centigrade. So, with this we will end today's tutorial lecture, and we will then move on to the last week of the course. We will talk about some more systems, especially the ionic solids and the glasses, diffusivities in them, and then we will also have a revision lecture. We will go through some of the important concepts that we discussed during this course, and end with the tutorial, of course. Okay, thank you.